Hello everyone, today we're gonna talk about the solution of homework 1. Let's look at first problem. So it asks us to find the dynamic and kinematic viscosity of 50. So what you can do is using the appendix in the textbook. Here we use the figure A2 to find the first two, which is the kerosene and motor oil here. So we find the temperature at 50 here. Then go down and find the motor oil, which is this line here. And find the cross here, and it will be at 4. So your number will be 4 times 10 to the minus 2 newtons times second per meter squared. That's your dynamic viscosity. And then you go down and find similar thing, which is for the kerosene here. It will be a little bit over 1, so I'll probably say 1.1 or 1.2 for the dynamic viscosity. Now let's look at the kinematic viscosity. It's similar thing, but the figure you use is A3. Here in the appendix, you'll do the same thing. Find the temperature at 50 degrees Celsius and go down to find the material you want and find the kinematic viscosity. Here is about 4.5 times 10 to the negative 5 power, and go down and find the kerosene. It's kind of at the end of the curve, so it's a little bit to find the correct number, but I would say it's about 1.5 times 10 to the negative 6 for the kerosene. And for the water, we have a summary table in the appendix. So it's table A5, and it has both the kinematic and dynamic viscosity at 50 degrees Celsius. So you can easily find the two numbers here. So let's write down the final answer for all of them. So for the dynamic viscosity for the kerosene, it's about 1.1 times 10 to the negative 3 Newton seconds per meter squared. And for the kinematic viscosity for the kerosene, it's about 1.5 times 10 to negative 6 meter squared per second. And for the motor oil, it's quite a long name, so I'll just shorten it to motor oil. So it's about 4 times 10 to the negative 2. Adding the units here, and your kinematic viscosity for the motor oil. It's 4.5 times 10 to the negative 5 meter squared per second. And for water, for the dynamic viscosity, you will have 5.47 times 10 to the negative 4 newtons per second, newtons times second per meter squared. And the kinematic viscosity for water is 5 times 5.53 times 10 to the negative 7 meters squared per second. Now let's look at the second problem. It asks you to find the pressure increase for the water to reduce its volume by 3%. So to solve this problem, we're gonna use the equation of bulk modulus of elasticity, which is E equals minus delta P times V over delta V. So first we're gonna find the E for the water, which gonna be 2.2 times 10 to the power of 9 Pascal. This is from the table A5. Okay, so then you plug numbers in. 2.2 times 10 to the power of 9 Pascal equals to minus delta P times V over minus 0.03 V. So you're gonna cancel out the V and find your delta P, which will be 0.03 times 2.2 times 10 to the power of 9, which will be 6.6 times 10 to the power of 7 Pascal. For the problem 3, it's a multiple choice problem. So it asks what is the correct statement for the non-slip condition. The A says only applies to ideal flows. That's not relevant to the assumption of non-slip condition actually. And for the second one, only applies to rough surface. Actually can apply to both smooth and rough surface. For the third one, mean velocity V is 0 at the wall, which is not correct because you could have a moving wall or a stationary wall. So either it can be 0 or it's the velocity of the wall. But if it's a stationary wall, that means the velocity of the wall is also 0. So the last selection D is correct because it says it's the velocity of the wall. Okay, so here is a kind of graph for this problem. You can see the non-slip condition actually is at both of the walls. One is moving, one is stopped. So it can be both 0 or at velocity V, but they both equal to the wall here and here. So for this problem, you choose D. Now let's look at problem 4, which is 2.32. So it gives us an equation for the velocity distribution which is U equals A times Y over B to the power of 1 over 6. Okay, now let's write down the equation for the shear stress, which is tau equals to mu times du over dy. So we have the velocity distribution u here, but we don't have the du and dy over dy, so we're gonna find it by using the derivative of, that's gonna do a derivative of u here. So du over dy equals to d over dy times the equation a times y over b to the power of 1/6. And you can move the a and the b out because they are constant. So du over dy equals to a over b to the power of 1 over 6 times d over dy times y to the power of 1 over 6. Now we're gonna apply the derivation rule, which gonna be du over dy equals to a over b to the power of 1 over 6 times 1 over 6 times y to the power of negative 5 over 6. Now we have a equals to 10 meters per second. B is 2 millimeter, which is 0.002 meter. And we're gonna plug numbers in, and du over dy will be 10 to the 0.002 to the power of 1 over 6 times 1 over 6 y to the 2. And we also ask to determine the shear stress in the water at y equals 1 millimeter here. So y is 1 millimeter, which is 0.001 meter. So we'll finally have a number of 1485. The units will be second to the power of negative 1. Okay, now we can calculate the shear stress, which is equals to mu times du over dy. And you can find your mu from table A5, which is going to be 1 times 10 to the 3 newtons second per meter squared times 1485 second to the power of negative 1. So you'll finally get answer of 1.48 newtons per per meter square, which is, you can also say it's 1.48 Pascal. Now let's look at the last problem. It gives us two walls. One is the top plate is moving with a constant velocity, and here it has a force of 1 Newton. And this problem asks us to find the viscosity of the fluid. And here we have a linear velocity distribution. So for the linear velocity distribution assumption, we can have here is the top plate moving at 22 meters per second, and we have another one which is fixed. Because of the linear distribution, we can assume the velocity distribution is look like this. We have velocity equals to 0 here. Okay. So this assumption will help us to find the du over dv. So then we can find the shear stress and then calculate the viscosity. Okay, so the shear stress tau equals to mu times du over dy. Okay. And we have our du over dy equals to 22 meters per second over 1 millimeter. Please pay attention to the unit conversion here. So we will have 22,000 second of minus 1 for the du over dy here. And now we need to find the tau to calculate mu. Tau is also equals to F over A here. So let's go back and look at the dimension of the plate, which is 50 millimeter wide and 100 millimeter long. So that's our A. Our F is 1 Newton. Our A is 0.1 times 0.05 meters squared. And this will give us our 200 Newton per square meter. So the mu will be tau over du over dy. Okay, 200 Newton per meter squared over 22,000 second to the minus 1 power, which will give us 9.09 times 10 to the negative 3 Newton second per square meter.